need the like physical. What is it called? Paper?
I guess we're gonna start. I guess just a couple minutes here. We're about to get started.
Yeah, I forgot that the thing is fast.
Get some more cookies real quick.
We'll wait until about 5 after, but please help yourself to refreshment and snacks. That's the other thing. I think we keep standing here and not starting.
I think we have to stand on like opposite sides of this one.
I guess so. Oh, I like the mug.
Oh, it's a temple mug.
Oh.
You should go downstairs. Have you guys heard about this?
No.
Oh gosh. Okay. It's a satellite that is measuring like ozone and all kind of like molecules over the U.S. with a resolution of like 2 kilometers, so they can go into cities and see pollution and that kind of stuff. Yeah.
Wow.
Temple, and it was built here. So, I mean, here, not here, like here at the CFA. So.
Right in this room, right here.
Yes. Oh, are they? Oh gosh, this is super cool. Like definitely, yeah.
Wow.
All right, guys. I guess we're gonna get started. Hello, my name is Jamar Kittling. I am a rising senior at Wesleyan University. Right now, my project is analytically investigating Leo 1 with Dr. Mila, and I am an astrophysics major.
Hi there, my name's Nadia Katab. I am a 6-year super duper senior at Georgia Institute of Technology doing research with the LIGO group, and I'm currently here at the CFA working with Dr. Razi Imami doing research in AGN jet feedback.
So, Dr. Mercedes Lopez Morales is an exoplanet researcher here at the Smithsonian Astrophysical Observatory. She completed her undergrad at the Universidad de la Laguna in the Canary Islands. Afterwards, she took some time away from academia to work in a planetarium, but her love of space and planetary science eventually led her back to graduate school at Chapel Hill, where she got her PhD.
After completing her PhD, she held 2 postdoctoral positions in Washington, D.C., one as a Carnegie Institute Fellow and another as a Hubble Fellow. Afterwards, she went back to Spain to work for the National Research Council in Barcelona. Then a decade ago, she came here to Cambridge to work at the CFA as a planetary research scientist. Recently, she's been appointed the acting associate chair of the CFA and has received many prestigious awards, such as being named a Radcliffe Fellow and receiving the NASA Achievement Award for establishing the dual anonymous review process to prevent discriminatory practices in grant funding distribution.
Her hobbies include hiking, enjoying new foods, and hooping on the court semi-professionally. She even used her basketball skills to coach kids in order to help pay for her college education.
Please join us in welcoming Dr. Lopez Morales.
Thank you, guys. That's awesome. Also, thank you, Jamar and Nadia, for the introduction. I mean, I must say, like, my college fees were like $400, so it's not here. It's not the same as here. And, and also, thank you, Matt and Jonathan, for inviting me to give this talk. So I acknowledge this was an official CFA colloquium that I gave last January, adapted for you guys, because I figured that some of you might have seen this kind of stuff in the news when it came out. It was about 6 or 7 months ago, but you haven't seen like the insider scoop of it. And if you haven't seen it at all, I will show you some of the exciting things that we have been doing with JWST for the past year. But like everybody, I don't work in an island. I was born and grew up in an island, but I don't work alone. So these are all the faces of people here at the CFA, my group, like current and past people here. And it is thanks to all these people that some of this work gets done. I mean, not everybody works on JWST stuff, but it is this group that basically helps me do the work that I'm going to tell you about. And also, so now you see the faces, so if you see them around, you kind of know what these people are up to. So going back into my talk, so basically, what I wanted to tell you is about what we are doing with exoplanets right now. I know that you guys are new to the field, so probably exoplanets sounds like an old thing to you, but when I started working on exoplanets, we only knew of 20 of them. For those of you who don't know what exoplanets are, I put together this video that basically shows you that for most of our history, we only knew of 8 or 9 planets in the solar system when Pluto was a planet. But back in the 1990s, we basically started to find these planets around other stars, which is what we call exoplanets. And here what you see with the different colors is the evolution of planet discoveries over the past, well, until 2021, basically, with the different techniques. And I know that some of you are doing work on exoplanets, so basically, for those of you who don't, I'm happy to explain the techniques a little bit more later if you want, but basically, the green points are red radial velocities, so that's basically the Doppler shift of the star, that's how we find them. The transits are just the geometrical orientation, the planet goes in front of the star from our point of view, so we see these little dips in light. So those are all the red points. And then these kind of yellowish ones, which you see them out here. And I know that Iceland works on this. So those are from microlensing. So for those who are sensitive to the ones that are farther away. And then direct imaging, those are these cyan colors. So you see that they're also way out. So one thing that you might notice in this figure as well is this, right? So most of the planets that we have discovered so far, they are what we call gas giants. If you look here in the vertical axis, and I just realized that that's on top of some of the values of the masses. So basically, that is one Earth mass, and all the way up there, all these red and green points, those are Jupiter mass planets. So those are about 300 times the mass of the Earth. So what you can see is that our techniques right now are really good at finding anything that looks like a Jupiter, a Neptune, But then, as soon as you get to the smaller planets, like what we call the rocky planets, those are planets the same size as Earth. What you see is we have found some of them. Most of them are candidates, but we have about 100 of them. But we haven't found anything like Earth, Venus, or even Mars or Mercury yet. So what we are doing right now is, and by we I mean as a community, what we are doing is, first of all, these 2 missions are up and running, so people keep looking for more planets, with the TESS mission from NASA and the Gaia mission from the European Space Agency, and then there is this other mission, the Nancy Grace Roman Telescope, which is planned to be launched in, I forget if it is 2025 or 2027. So that's from space. So these are missions that are going to continue looking for planets. And then from the ground, we are building all these, extremely large telescopes in the next decade. And these telescopes are going to have these instruments that are actually designed to look for exoplanets. So if you spring forward, this is what we think is going to happen in the next decade or so. So if you remember before, we had about 23,000 planets, which I must say, those are candidates. Confirmed exoplanets, we have about 5,000. But then, spring forward a few more years, 2026, and we expect to have about 41,000. Spring further into 2030, and we expect to have about 85,000. So if you just imagine that we can confirm only 15 to 20% of those, we basically will have about 15,000 planets. So, and also, we expect that at this point, by 2030, we will still not have found anything like Mercury and Mars, but we already will have some candidates for Earth or Venus-like planets, like right temperature, right size, like proper terrestrial planets. So it is exciting. So you probably have heard, a lot of people telling you this, that we're looking for more planets, and we're looking for planets like Earth. So this is kind of like a race to the bottom. The smaller the planet I find, the more famous I am, kind of thing. And that's kind of cool science, and I'm part of that race just because it's fun. But now we basically have so many planets that a fraction of the community, people like me, we're basically saying, okay, so enough counting planets. This is all these planets are super cool, but what are we doing with them? We really want to start understanding the physics and chemistry of these things. So what we are doing, dear people like me working on atmospheres, is we are trying to figure out properties of planets, like, and we have some very big questions that we don't have answer to. Like, we know nothing about it. Like, one of those big questions with this like fancy picture here is, how do planets form and how do they evolve? So, as you see here, there could be a star forming, and this is like a disk, of gas and dust and stuff like that, where the planets are forming. We really don't know how that happens very well. Like, people do disks, but we can't really see the planets, so we don't know how they form, where they form. How do you get a hot Jupiter with a period of like 4 days? That's impossible to form anything in there. So how do they form and evolve? We have no idea how that happens. Another thing that we don't know is, what are the planets made of? Because all we do when we find them, I was telling you about Jupiters and Earth and Neptunes. That is because when we find them, all we measure is how massive they are and how big they are. And that gives us a density, so you know if it is a gas giant like Jupiter or if it is a rocky planet like Earth, but that's all you know. We really don't know what the planets are made of. That's another big question that you will see a lot of this in the talk, you'll see. And another thing that we don't know is how diverse exoplanets are. And by that, what we mean is, we have only characterized planets in the solar system, but we don't know what everything else is made of, and we actually don't know how our solar system compares to everything else that we're finding. So, is the solar, are the planets in the solar system like something unique? Are the planets in the solar system something very common? We have no idea. So all these questions, you can actually answer them by studying the atmospheres of exoplanets, which is what we do. And just to give you a little bit of a historical context, I like to show this slide just so you see, you understand, the time that we're living in. Okay, I'm not joking here. This is super cool. So you guys have probably heard here this story about the Harvard computers, right? Now, they were like this group of women that we actually had that telescope in there, well, actually that telescope, that had a spectrograph, and they were taking a spectra of stars, and and they were analyzing, and they were looking for these absorption lines, all these things, and eventually they figured out, this was Cecilia Payne, who was one of the Harvard computers here. She figured out that those lines correspond to hydrogen and helium, and in her PhD thesis, she basically said, stars and the sun are balls of hydrogen and helium. And then they have a little bit of sprinkles of iron, carbon, oxygen, you name it. So those, we call them metals. I don't know if you guys have gathered that one already. So everything that is not hydrogen and helium is a metal for us. So, but this was, her PhD thesis was in 1925. So this was 100 years ago. So right now, what we are starting to do right now, what you guys are witnessing, is the same story with exoplanets. So we are trying to develop, the HR diagram of exoplanets, how does the spectrum of exoplanets looks like, and you guys are witnessing that right now. So that's what we are doing. So the question is, that's super cool, but how do you do that, right? So we basically have two main techniques that are divided into 4 things, but I will just explain this to you briefly, so then I can explain how do we actually measure the things, right? So there are 2 main techniques right now. This technique is called direct imaging, and the name just says it. Basically, we figure out how to block the light coming from the star with a coronagraph or something, and then we look around it, and we try to see these little dots of light. Those are planets, and if you can get a spectrum of a planet, you can figure out what the planet is made of. Super cool. This is where we are going. We don't quite have the technology to do that yet. So how do we do it right now? So there's this other way to do it, which is basically, it takes advantage of the transiting planets. And these are, planets that, because of their orientation, as I was telling you earlier, they go in front of the star and behind the star, and they produce these little eclipses, right? So there is 3 ways to study the atmosphere of an exoplanet that is transiting. The first one is that thing with the dark red circle in it. That's called transmission spectroscopy. It's a mouthful, But basically what it means is when the planet goes in front of the star, the atmosphere is kind of translucent. So part of the light from the star percolates through the atmosphere, but then some colors actually interact with the atoms and molecules and clouds and in the atmosphere. So you basically lose some of it. And you only see the light that is transmitted. So that's why it's called transmission. You also have the same, a similar technique, but now it's when the planet goes behind the star. So then you basically look at the star while the planet is, outside, like the star's line of sight. And then, so you see a certain amount of light. When the planet goes behind, you lose that light. And then you measure the colors of the lights that is missing, and that's the spectrum of the planet as well. So that's called emission spectroscopy. And then another thing, if you see that white line going around, that's what people call phase curves. And this is like the phases of Venus. So when the planet goes around, you basically see it at different angles. So you see it in different phases. So if you sit on the system and you monitor it, you basically see how the light from the planet is changing, and you can see what's the composition of the atmosphere in the different parts of the planet. Those results are not out yet. But we have them, and they're super cool. So the results that I'm going to show you about actually focus on this transmission spectroscopy, like when the planet goes in front of the star and the light goes through it. So those are the results I'm going to show you about. So this is cool, but how do we actually measure a spectrum, right? So this is a little bit complicated. I'm happy to explain more later, but just, I'll try to explain it quickly so you guys get the idea. So you basically have the planet goes in front of the star and produces an eclipse. That's what people call a transit, right? So each one of those depths is a transit, but it's a transit in a different color of the light in the spectrum. So if we step back a couple steps, we basically wait for the planet to go in front of the star, take a spectrum, and we just monitor it. So we take a sequence of spectra, and then we take our sequence of spectra, and we bend it into chunks of different colors, and then we plot the transit light curve, which is like how much light from a certain color are you getting as a function of time. And as you guys can see, first of all, the different colors give you a different shape. And that's because of the edges of the star. That's the limb darkening. I don't want to complicate much. But what is important here is that different colors give you different depths. And that's because depending on what the atmosphere is made of, certain colors of light absorb, certain molecules absorb certain colors of light. So then, say, here, for example, at 1.4 microns, water absorbs at 1.4 microns. So if you look at that color, the planet looks bigger. And if you look at that color where the light just goes through, the planet looks smaller. So that's what we do. I mean, it's fairly simple, but I will explain to you how it gets complicated. So we basically look at how that depth changes, and we plot it, so this is the transit depth on the y-axis there, and we plot it as a function of color. And that's our spectrum. And you will notice that in this case, because it is an absorption, the planet gets bigger. So this is kind of the opposite to the spectrum of a star where you see absorption lines. Here it's you take that absorption line and it's shifted upside down. So an absorption line would look like a bump in here. So basically, that thing that you see there at 1.4 microns, that will be absorption by water. And that's how we do it. That's all we do. Now, this is the catch, right? The catch is do you see that number there? The change in the transit depth is 0.01%. So most of you, if you have an error bar of 1% in your result, you're like, oh my God, this is great. So we are trying to get to precisions that are a factor of 100 for Jupiter's, a factor of 10,000 for Earth, below that. That's where things get complicated. So we are basically looking at 1 photon per every 10,000 is missing from here, from this depth. If you have a Jupiter, if you have an Earth, we are looking at 1 photon per every million is missing. So that's where it gets complicated. So for the past 20 years, we have been trying to detect that 1 photon per 10,000, 1 photon per million, like with everything that was available, you name it. Hubble Space Telescope, Spitzer Space Telescope, the Magellan Telescope, the Keck telescopes, the VLT. And the problem was that none of these was actually built to achieve this kind of precision. So we literally spent, I would say, 90% of our time like trying to remove noise from the data from all these instruments, so we actually could see like the little changes in the transit depth. And this thing that I show you here, so over, I would say like 15 to 18 years, we managed to measure the transmission spectrum of about 60 planets. That's it, of the 5,000 that we know now. And this is just a sample of 10 of them, just plotted here. So the dots are the data, and the solid lines, those are models that we fit to the data. And here, like this figure, if you have seen like a, gosh, I forget the name, like a diagram with all the spectral types of the stars, of different, like.
Chart diagram?
Is that a chart diagram? Yeah. No, it's not a nature diagram. It's like the spectrum. Like, so you basically show the spectra of like O type stars and B, and you see, all the way down to M type stars, and you see how the spectrum. Anyway, I can't remember it. If I can remember the name, don't worry about it. So this is kind of trying to do a similar thing with exoplanets, except that when you actually make that figure for stars, it's clear that the shape of the spectra in the stars actually changes as a function of temperature. Here we have no idea what controls all these changes in shape. Like, yeah, I will explain to you a little bit what is shown here, because later I'm going to show you some more of these things. But you basically see like, like these bumps at 1.4 microns, that's water. These little spikes here, that's potassium. That little spike there is sodium. That slope tells you that you have a haze in the planet. The larger the bumps, that tells you that the planet is clearer or has more water in it. So this figure is made in such a way that we just try to see a sequence. But one thing that we have found, and so this is the big result up to like 2021, okay? Is we basically have found that about 7% of the planets that we observed are clear. Everything else has clouds, which if you look at the big planets in the solar system, it's kind of the same. So, everything has clouds. Another thing that we have found, if you see here, is that water is everywhere. So all these planets seem to have a lot of water, which I will explain to you later why that is important. So the early models from the 2000s actually predicted that these planets should have sodium and potassium absorption. And that's because the models of these planets were kind of like mimicking the models of brown dwarfs. And brown dwarfs of about this temperature, so this is like about 1,000 Kelvin, they have sodium and potassium lines. So here, some of the planets have it, some of the planets don't, and we don't know why that is. And then, so we have no idea what controls the different parameters for the planets. Like temperature seems to be doing something, but it's not clear. Irradiation from the star, metallicity of the system. We just don't know what controls the property of the planets. And another thing that I will show you next with the new data is that we could only observe things down to about 1.7 microns. So we could only do like those two atoms and water, but there's a lot of stuff out here, like a lot of molecules out here that we couldn't do. And that's why we say here, and I will explain later, that we could not constrain the carbon to oxygen ratio. And that's important, and I will explain to you why later. So this is where we were in 2021. And we were stuck. Like we just didn't have, like any other instrument to do anything. And then the James Webb Space Telescope launched on Christmas Day 2021. And the first data came on July 12th, 2022. So this is like almost like a year to the day from today. And this was a game changer. I mean, I'm just gonna show you here briefly. Is that? Yeah, so here just briefly as an schematic, just to give you a couple like a couple ideas of to why this was such a game changer, right? So the first thing is, with Hubble, that was the best telescope that we had, we could only get down to about 1.7 microns. With JWST now, and those are different instruments, we can go down to almost 30 microns. So just that is a factor of 10, like in wider coverage of, of colors, of wavelengths. So that on itself is a game changer. Another game changer is that Hubble is 2.5 meters in radius. James Webb is 6.5. So the ratio of the areas is a factor of 7. So immediately you are getting at least 7 times more photons. Big plus. And the biggest plus is that James Webb was built to observe exoplanets. So all that noise, all those systematics that we were always like battling, they're gone, they're gone. So that was a big deal. Another big deal is that when they were building JWST, they already have exoplanets in mind. And even before the telescope launched, we already had data, like they had already scheduled to get data for 60 planets. Remember the number? Those are the same number of planets. It took us like 18 years from the ground. And JWST was going to do this just in 1 year. So 60 different planets scheduled even before the telescope launched. So that was so they obviously did other programs as well, in cosmology, planetary science, galaxies, everything. So they allocated, even before the telescope launched, they allocated 10,000 hours of telescope time. About 25% of those were allocated to exoplanets. That's a total of 104 days. And I'll explain later why that number is important. So here, what you see here is just a diagram with like the size of the planet versus the temperature of the planet of all the planets that have been scheduled as of last year. Like now with cycle 2, we actually have twice as many. But this was up to last summer. So we had 60, and you see that we have like all kind of planets scheduled to observe, like hot Jupiters, like big things like Jupiter with temperatures of like up to like 2000 Kelvin. Things that are cooler, actually like Jupiter. Then we have these things in the middle that I don't know if you guys have heard about, this super Earth stuff. That is like planets that are kind of like between the size of Neptune and the size of Earth. That it turns out that they're the most abundant planets in the galaxy, but we don't have them in the solar system, so we have no idea what they're made of or how they work. And then we also have smaller planets, like Earth-sized planets, of all different temperatures, like things of a similar temperature as Earth. These things called lava worlds that are like small planets that in principle they are like rocky planets as well, but they're so hot that the crust of the planet is like a magma ocean, and so all kind of stuff. And so what I'm going to show you here is just 2 examples, because otherwise, I will be talking for a whole week. But I'm just going to show you two examples of planets that we have been involved in. And I mean, yeah, another thing I forgot to tell you is that of the 60 planets, our team here is involved in the analysis of 25 of them. And these are 2 that we have been involved in. The first one up there is a hot Jupiter. That's kind of like a classic, but we still didn't know how they worked. And this one here is actually the first terrestrial planet observed with JWST. So this is where things get super cool. And now, so this part is going to be a little bit more technical, I think. So if you guys have questions, like please interrupt, because I don't mind. So the first planet that I was mentioning is this hot Jupiter that we call it WASP-39b, which is the phone number. But basically, so it is a planet that is 30% bigger than Jupiter, but it's actually the mass of Saturn. So this is like really puffed up, like low density. And it has a temperature of about 1100 Kelvin. And this data that I'm showing you here, these are Hubble data. And what Hubble, like this is Hubble and some data from the ground as well. And these are 2 Spitzer points. And this is like the best spectrum that we had before the launch of JWST. And you see here that we clearly saw water, we saw a little bit of potassium there, kind of saw sodium there. And we also saw that, so those features are like super bumpy. So that basically means that that planet doesn't have a lot of clouds, because otherwise all these features would be like totally like washed out. So this is why this planet was selected to be the first one to be observed with JWST, because we thought, oh gosh, you know, if we can extend the observations into the infrared, we're going to see a lot of stuff. And yeah, I'll tell you about this a little bit, because this is where we're actually doing physics, you know, and chemistry and stuff like that. So with the data that we have from HST, what we could tell is that the planet had an atmospheric metallicity of 151 times solar. I will explain. What that means is that if you look at the ratio of how much hydrogen and helium you have in the sun versus all the other elements, what we call metals, that ratio is whatever, say it's a ratio of 1. So this planet, from these original observations, seemed to have 151 times more metals, or more everything else than hydrogen and helium. And this figure here shows you the amount of metals in the planet atmosphere versus the mass of the planet for the planets in the solar system. And this one was 13, yeah, and then, you know, a couple other planets that have been kind of constrained, but as you see, the error bars are very large. And then this planet was like all the way up there, like off the charts. And we had no idea, like, how do you form a planet like that? Just a preview. So we took it to JWST, and we observed it with all the instruments on JWST. And you know, as you see from the days, like this was like 3 weeks of observations, you know, and it wasn't like 3 solid weeks. It was just like 4 transits. So the total amount of time was 40 hours of data, of which half of that time is just the telescope getting to the target and doing things. Like so it's really, the science data is about half of that time. So it's about 20 hours, maybe 24 hours, something like that. But we basically took data over all those wavelengths with 4 different instruments. And what I'm going to show you now is, you know, I realize that this is a lot of information, but I wanted to give you a snapshot of what we saw from those 4 instruments. And the first thing that you see is that you basically have like a lot of more points, you know, and the wiggles are a lot clearer. And there's a lot of stuff there. So I'll help you. So we see potassium, we see water, we see sodium. I'm not going to give you a sneak peek of that. We see carbon dioxide and so on. So why is this important? Okay, so what I'm going to do in this like last third of the talk is basically going through most of these molecules and actually try to explain to you like why we are so excited about it and what are they telling us about the questions that I was asking you at the beginning. You know, like, how do planets form? How do planets evolve? What are planets made of? You know, how do they compare to planets in the solar system? I want to show you like 4 molecules that we found, and I'm going to tell you the story of what they are telling us, and it's super cool. All right. Oh, and I forgot to say, like, this stuff is producing like Nature papers like peanuts. So at the time when I gave this presentation in January here, we had 6 papers submitted. Now we have 3 more, and we have an arrangement with Nature to publish 13 of them. So, and they gave us a 50% discount on the price. So that, I'm happy to tell you guys about that as well. But anyway, so this is like super cool stuff. This is like press releases, Nature papers, like super exciting. Anyway, so let me tell you the actual science now. Like, forget about press releases and paying for paid charges and stuff like that. So the first result, water and CO2. Okay, water is that, well, and let me explain to you briefly as well. So again, like the black dots, that's the data. And the yellow, pink, and blue lines, those are 3 different models. Like we used like from 3 to 7 models, depending on the data set, like independent models to fit the data. And the whole point of showing the models here is that they all agree. They all find the same thing. And what we find is water, given by that slope in there. And that's not a big deal because I already told you that with HST we have water. What's a big deal is that now our detections are like 22 sigma. Before, if we got a 5 sigma detection, we were having a party, okay? So 22 sigma, and not only that, but we see the water like everywhere, in all 4 instruments. Like, there's no doubt that we have water there. Another thing that was super shocking to us was that bump in there. Like, honestly, this took as soon as the data came out, we just looked at it and we went, carbon dioxide. Like, we knew it. And this is almost like a 30 sigma detection. We didn't even need a model for that one. And this thing that you're seeing here, guys, this is the first detection of carbon dioxide in a planet outside the solar system. So, and the reason why I'm showing you these 2 things together is because, remember I was telling you about this carbon to oxygen ratio? So, water and carbon oxide molecules are the main molecules where carbon and oxygen form, okay. They're the main molecules that those 2 elements form, in an atmosphere. So if you can measure how much carbon you have versus how much oxygen you have, you get a pretty good idea of where this planet formed. And so here, just so you keep it in mind, so the carbon to oxygen ratio of that planet is between 0.3 and 0.46. And I will explain to you why that's important. And another thing that you notice now is that the metallicity that we find is 3 to 10 times solar. It's not 150 anymore. This is good news. So I will explain to you now why the carbon to oxygen ratio is so important and so cool. So the planet appears to have from 0.3 to 0.46. The star itself appears to have 0.58. So basically what that means is that both the star and the planet have more oxygen than carbon. But the planet is enhanced on oxygen. So the planet has more oxygen than the star. What that means for formation is, I don't know if you guys have heard about these, ice lines or ice, it's ice lines, right? So, okay, for those of you who haven't, the current thinking is that when planets form, they obviously form from this disk made out of gas and dust and so on. And as the star, so the star is in the middle, and the radiation from the star is blowing the gas and the dust from the disk away. So anything close to the star is kind of like a void, right? It's like there isn't a lot of stuff there, but as you get farther out, things get colder. So at some point, you get to the temperature where water condenses. So you should have a lot of water there, and then so that's called the water ice line. So basically, what this graphic shows is, if that's your star, that would be the distance where water is stable now. Anything further in is not stable. That would be the distance where ammonia is stable. That would be the distance where carbon dioxide is stable, and so on. So for that planet to have more oxygen than carbon, it must have formed in that region. So because it needed to have water to accrete into the disk needed to have water to accrete into the planet, but it needed to have more oxygen than carbon. So it wasn't here, and it wasn't here. The planet formed in that region right there. And that's super cool because that's the current theory that said, because right now, all these hot Jupiters that we are finding really close to the star, we're like, how in the world can you form those things that close? And one of the driving theories is oh, you know what? They actually form farther out, and they migrate just because of friction. And one way to prove it is to look for things like water and carbon dioxide. And if you don't have a lot of oxygen, then the planet must have formed in here. So that result actually is showing that, yeah, the planet formed where we think it formed, even though now it's at a period of only 4 days. Now it's right here. So this is proof that our migration theories actually work, and it's what we think it is. Second thing is a similar thing. It explains the same concept, but in a different way. And it's, I don't know if you remember when I was showing you the plot with all the Hubble spectra, that I was saying sometimes we see potassium, sometimes we don't, and we have no idea why. Well, so in this planet, we couldn't find potassium with the Hubble data. And with the JWST data, there's this really nice potassium band in there. And, and this is done with another instrument from the one that from the other spectrum that I was showing you before. And again, these are the observations, and then each one of those color lines are different models, where what people did in this paper was we measured the amount of potassium, and then so that spectrum obviously goes farther out, and it also has water. So we could measure how much potassium versus how much oxygen we had. And we basically get this number that is like 0.4. It's like that kind of like this line is kind of the one that fits the best. So that is higher than the potassium to oxygen amount in the star itself. So what this is telling us is, again, it's telling us that the planet had to come from outside, from outside the water ice line, and it migrated in, and then sodium and potassium, they are called these alkali elements. So they actually condense in these little rocks that can be closer to the star, and they're just floating all over the place. So for the planet to have more potassium than the star, this planet must have migrated in, and as it went in, it accreted the potassium, like all the little rocks that were in the disk, and that's how the planet got a lot of potassium. So that's also a second proof that that thing formed outside and came in. So super cool. And this was also a theory that was published in 2022, and it was proven a few months later. So I'm pretty sure that these people are super happy. Okay, a third one, a third discovery that I think, if you were paying attention before I gave it away. But the mystery molecule, this was we had no idea what this was, and it's super cool. So, it might not be obvious to you guys, but to the trained eye, we kind of saw it, and we were like, what is that? So I don't know if you see here, around 4 microns, that there is the model and the data don't really fit. The data goes up and down like that. And we were like, what is that? What is that? And none of the models that we were using could fit it. And then so we basically have this is a team overall of about 120 people across the world, and there is more than 20 theorists. And all the theorists were like, what is that? This is crazy, we don't know what it is. And then this guy, Shamit Sai, he's like, it's sulfur dioxide. So, and so this was such a cool discovery, both because this guy, Shami, he had a model that used photochemistry, which nobody else did. And the second thing is that, I see Vladimir here, Hydron team, SAO. So all these lines came from the Hydron, all these SO2 lines came from the Hydron team here at SAO. Everybody was just guys, we need lines of SO2 within the data set. So thank you to the Hydron team. I mean, this was a super cool discovery. And so why is this so cool? Well, so, if you guys think of the ozone on Earth, ozone forms, you basically have a lot of oxygen, and then, oxygen just floats in our atmosphere, and the ultraviolet radiation coming from the sun splits the 2 oxygen atoms into 2, and you have all these single oxygen atoms going around, and they condensed into 3 atoms, and that forms ozone. And thanks to the ozone layer, we are alive, right? So photochemistry is super important, and we know that on Earth is responsible for things like habitability and all these things, right? We have never seen photochemistry in any other planet anywhere else. So this is the first detection of photochemistry in another planet, outside the solar system. And so this is basically this reaction here, which, I'm not a chemist, so please don't ask me. But basically, so the net reaction is basically, so sulfur hydride, gets hit by the ultraviolet radiation coming from the star, and then it combines with water, and obviously those photons, and then it ends up with 3 atoms of hydrogen and SO2. So photochemistry seems to be happening everywhere. And if it is happening in just some random Jupiter that we were looking at, probably other planets out there like Earth also have photochemistry, so habitability is a possibility. So that's why we were so excited about this. And I must say as well, like, SO2, volcanoes on Earth produce SO2 because they put out a lot of sulfur and stuff like that. This is not a habitable planet, okay? This is a gas giant, with no solid surface or anything like that. Because, some reporters were like, oh my God, volcanoes. And we're like, no, this is not volcanoes, okay? This is just a gas giant where photochemistry is actually happening. So photochemistry must be ubiquitous, like everywhere. And that's why this result was so cool. And not non-result, okay? Because you always show the things that you find, but you never show the things that you don't find. But this non-result is as important. Methane. We don't see methane anywhere. And so you see that here, so you basically have all the dots are the observations, and then all those different shades of pink are models where, we basically change a bunch of things. Like we change metallicity of the planet, we change the CO ratio, we put clouds in, we take clouds out. And there is no way that the spectrum has that, that thing there, that peak is called the methane finger at 3.3 microns. That's a very well-known feature. And we don't see it anywhere. So whatever is happening in this planet, we don't see methane. And actually, so the reality is that because the planet is metal rich, I don't know if you guys remember that we were saying that this is about 10 times the metallicity of the star. Because the planet is metal rich, what that means is that it has a lot of oxygen and carbon. So because the oxygen is there, then the carbon combines with the oxygen instead of combining with the hydrogen. And that's why you don't see methane. So if we had a planet where you took all the oxygen away, the carbon that is left would combine with hydrogen, so you would have methane. So this is all consistent with the picture of the atmosphere of this planet is about 10 times solar. Oh, and one thing I forgot to tell you is this. So 10 times solar is the same metallicity as Jupiter, like our Jupiter. So that means that this planet probably formed the same way as Jupiter, which is also another theory that is kind of proven now. It's just so there's two theories for how planets form. One of them is core accretion, and the other one is instability collapse or something like that. Sorry. So the core accretion, basically, the idea is that the heavier things in the disk accrete first, and then gravity grows, and then that starts accreting other things, and that's how planets form. And the second theory, disk instability, is just things collapse as a clump, like that, like the star and the planets, and everything collapses at the same time. So if you can measure the chemical abundances in the planet, it tells you if it is one theory or the other. Because if everything collapses from the gas at the same time, then the star and the planet should have the same composition. But if the planet starts collapsing first by gravity and then accretes a lot of stuff, then the planet should have more metals than the star. And that's what is happening. And that's how we think that Jupiter formed. So this planet formed the same way. So this is all for what's 39. So just one planet, a day of data, has basically told us more about how gas giant planets form, honestly, in a month and 20 hours of data than the previous 18 years trying to do this. So super cool. And yeah, so this is a summary of the findings that I was telling you. So for the sake of time, because I really want to show you, the next thing is, okay, so I'm going to show you the results about the Earth planet now. And so this is again, it's a planet the size of Earth, with a temperature of about 600 Kelvin, which is about 600 Fahrenheit, 300 Celsius, and so this is a different program that we're also part of. That what this program is doing is trying to figure out if rocky planets, like Earth-sized planets, around M-dwarf stars, which are stars that are smaller than the sun, if they actually have atmospheres. And that's a big topic right now, because Well, first of all, like, M dwarfs are about like 70% of the stars in the galaxy. They're smaller than the sun, and then they're about like from half the size to a tenth of the size of the sun, and they're nearby. So just because these stars are a lot smaller than the sun, this is where we are finding all the rocky planets, just because it's easier, like the ratio of the masses and the sizes is smaller, so it's easier to detect the planets that way. And with current technology, as I was showing you at the very beginning, like until the 2030s, we are not going to find a planet around a star like the sun. So this is where we are looking for the habitable planets. But for those of you who actually work in stars, you probably know that M dwarfs are super active. Like, they put out a lot of like ultraviolet irradiation, a lot of X-ray radiation. So right now, people think that probably because of everything, like the star is blasting the planet so much that probably the planet cannot retain an atmosphere, unless it has things like a strong magnetic field and stuff like that. But that's a currently open question. Like, we don't know if these planets actually can be habitable, because if their atmosphere is like stripped away, these are like bare cores in there. So this is what this project is trying to do. And what I'm going to show you here is the first planet for which we got a result on this. So this planet was discovered by TESS, and this was the discovery data. So we weren't even sure that this was a planet, right? And so we observed it with JWST over 2 visits. Like, they gave us time for 3 visits, but one of them actually failed, and it's still being rescheduled. I think that they told us that they are going to observe in December this year. But with 2 transit observations, we actually got like really good data. And then here we did exactly the same thing that I was telling you at the beginning, right? Like, we took the spectra at different colors, we measured the changes in transit depth for all of them, and we got a transmission spectrum. So those points there, that's how the transmission spectrum of this like a terrestrial planet looks like. So as you can see there, like, we don't see any wiggles here. Like, this thing is super flat. And those models that I'm showing you here, so those are models for planets that have hydrogen. So one thing that we show here is that this planet is rocky. It's not some gas ball like Jupiter. No, it is rocky for real. And also we show that the planet is actually a planet, because from the test data we weren't even sure. But then, if you zoom in, if I go back, so see that gray band that I'm showing, horizontal. So, if we zoom in, on the y-axis, this is how it looks like. So we basically said, okay, this doesn't have any, any hydrogen or anything. But if you actually look at other models now, like, so basically we went in and tried to fit models for things that look like Titan, Venus, Earth, and Mars. What we discover is that, it doesn't look like Titan. Like, it doesn't have a lot of methane. So that's like that light purple line there, that you see that it doesn't align with the data very well. But then that's all that we can tell. Like, at this point, we can only tell that this thing doesn't have any big hydrogen atmosphere. It doesn't look like Titan either. But then, anything that looks like Venus or Earth or Mars, or even just like a flat, bare core with no atmosphere, all that is still allowed. So this is just to show you that with terrestrial planets, JWST needs, still a lot of work. Like, this is where things are being like difficult now. So this is my last slide. And so here, I just wanted to go back to the slide that I showed you with like all the planets that were scheduled to observe with JWST. Just to summarize, so this is all going to be observed by the end of this year. And there are a lot of these papers are already in the pipeline. I just didn't have time to show you everything. But then, so these 2 results that I've shown you here, this is about only like 2% of all the data that are available right now. And you see already like the kind of things that we can answer. For gas giants, oh gosh, like, we are going to be able to answer everything. Like, all these questions of like, how do they form? What are they made of? How diverse they are? How do they compare to planets in the solar system? That's going to be answered probably within 2 or 3 years, probably. The ones that are going to be difficult here are the Earth-like planets. That's going to take a lot more work. And probably we will not be able to, I would say that we probably can do the hotter ones, but something that is like truly like an Earth twin with the same temperature, same size, that's going to be tough. So if you guys are interested in this kind of topic, and since you guys are like younger than me, maybe you guys are going to be the ones that actually measure the atmospheres of these planets. And then we can add a question here that says, not how the solar system looks in comparison to other planets, but how does the Earth look in comparison to other Earth-like planets? So maybe there is no Earth 2.0, or maybe there is thousands. So with that said, thank you for listening, and I'm happy to answer your questions. Thank you.
All right, I guess it's time to take some questions.
Anything.
I guess I have a question.
Yeah.
So you're saying that it's hard to find atmospheres around Earth-like planets. What about super Earth type planets?
Oh, yeah, so those are easier. Yeah, so I didn't mention that, but yeah, so these ones here, they're obviously, their atmospheres are like a factor of 10 times smaller than the Jupiter's, but they are also a factor of 10 times bigger than the Earth. So those, we already have some data. They are looking a little bit cloudy, which is a problem because if you have clouds, you can't see through the atmospheres. But those are going to be resolved. Like how super Earth look like, we'll probably, in another 5 years, we can probably say this is how super Earth work. So yeah, and how they form and how they evolve and all that kind of stuff. So yeah.
This might be a silly question,
No.
but I am very curious.
No silly questions.
So based on your projections at the beginning of how rapidly our understanding of planets and exoplanets is expanding and how we're expecting to understand so many more in the coming decades, how long do you think it'll be until we find aliens out there?
Oh gosh, that's a good question. Oh, well, so, okay, no, but this is a really good question. So one thing I didn't mention here, and it's something that I work on as well, is so with all the technology that we have right now, we cannot detect oxygen yet. So that's one component, right? That's like to find Earth twins, or to find planets that have life on them, the way we know it at least, you also need